January 16, 1943, Portland, Oregon. The Swan Island shipyard was not sleeping. It never really slept. Under the harsh, bluish glare of the sodium floodlights, the facility hummed with the suppressed energy of a war machine running at maximum capacity. But at 11 p.m., the frenetic pace of the day shift had slowed to the slightly quieter rhythm of the night watch. The air was frigid, a damp, penetrating cold typical of the Pacific Northwest winter, hovering around 23 degrees Fahrenheit, -5 degrees Celsius. The Willamette River, black and oily, slapped gently against the pilings of the outfitting dock. Moored at that dock was the SS Schenectady. She was hull number 1, the very first T2 tanker built at this specific yard, a massive steel beast designed to carry 140,000 barrels of fuel oil to the desperate theaters of the Pacific War. She was, for all intents and purposes, a brand new car with 0 miles on the odometer. She had completed her sea trials earlier that day. Her gray wartime paint was flawless. Her bilges were dry. Her crew was ashore or sleeping, waiting for the final provisioning orders. She was floating in calm inland water, miles from the nearest Japanese submarine, seemingly safe in the heart of the American industrial fortress. Then the air tore apart. It wasn't a creak or a groan or the slow tearing of metal that one might associate with a structural failure. It was a report, a sonic boom. Workers in the administration buildings, nearly a mile away, felt the windows rattle in their frames. The security guards on the perimeter patrol dropped to a crouch, weapons drawn, scanning the darkness for the flash of a saboteur's bomb. The sound was dry, sharp, and deafening, like a heavy artillery piece firing at point-blank range. On the dock, the confusion was absolute. There was no fire. There was no smoke rising from the holds, no smell of cordite, just a terrifying, unnatural silence that followed the explosion. The floodlights swept over the ship, and what they revealed defied the basic laws of naval architecture. The Schenectady had not been attacked. She had committed suicide. A fracture, clean and jagged, had ripped through the thick steel plating of the deck, just aft of the bridge superstructure. It hadn't just cracked. It had separated. The breach ran down the port side and the starboard side, slicing through the hull plates as if they were made of brittle porcelain. With the structural spine of the ship severed, gravity took over. The immense weight of the bow and the stern, no longer supported by the keel, sagged into the water. The midships, relieved of the tension, rose grotesquely into the air, jackknifing the vessel. The ship slammed into the riverbed mud, her back broken. The gap in the deck was massive wide enough for a man to walk through, exposing the twisted guts of the ship, severed electrical cables sparking in the dark, steam pipes hissing as they vented pressure, and the raw, bright metal of the torn steel shining under the lights. In less than 10 seconds, the pride of the Swan Island yard had transformed from a state-of-the-art tanker into a pile of scrap metal. This catastrophic failure, happening in still water with no enemy action, was the nightmare scenario for the Warshipping Administration in Washington. But to understand the sheer terror that the Schenectady incident instilled in the Allied command, we have to rewind the clock. We have to understand that this ship was part of the greatest industrial gamble in human history. A gamble that, by 1941, the Allies were losing. The backstory of the Schenectady begins not in a shipyard, but in the freezing, submarine-infested waters of the North Atlantic. By late 1940, Great Britain was fighting for its life. The Battle of the Atlantic was not a battle of glory. It was a battle of arithmetic. It was a tonnage war. Britain was an island nation that imported nearly 1 million tons of material every week to survive: food, oil, aluminum, steel. The German Navy, the Kriegsmarine, understood this vulnerability perfectly. Admiral Karl Dönitz, the mastermind of the U-boat fleet, had calculated the equation of defeat. He didn't need to invade England. He simply needed to sink ships faster than the British could build them. The math was brutal. In 1940 and 1941, the U-boats operating in wolf packs were slaughtering the merchant fleets. They were sinking hundreds of thousands of tons of shipping every month. The British shipyards on the Clyde and the Tyne were working under blackout conditions, bound by the Luftwaffe and hampered by outdated methods. They could not keep up. The ledger of the war was bleeding red ink. For every ship launched, 2 were being torpedoed. Britain was months away from starvation. In desperation, a British purchasing commission was sent to the United States. They arrived in Washington with a blank check and a plea. Build us ships. We don't care what they look like. We don't care how fast they are. We just need them to float. The result of this plea was a design that would become legendary for its ugliness and its ubiquity. The EC2SC1, the Liberty ship. The design was an antique. It was based on a British tramp steamer concept from 1879, developed by the firm J.L. Thompson and Sons of Sunderland. It was the maritime equivalent of a dinosaur. At a time when modern naval vessels were sleek, turbine-powered, and fast, the proposed Liberty ship was a blunt-nosed, flat-bottomed box. It was 441 feet long and 57 feet wide. It was powered not by a modern diesel engine or a high-speed steam turbine, but by a reciprocating triple-expansion steam engine, a piece of technology that was already obsolete when the Titanic sailed. Why choose such an archaic engine? Because it was the only thing American industry could mass-produce without retooling its precision factories. Turbines required gear-cutting machinery that was already fully booked making engines for Navy warships. A triple-expansion steam engine, by contrast, was a hulking mass of cast iron that could be built by any foundry that made farm equipment or locomotives. It was 2,500 horsepower of reliability. It shook, it rattled, and it topped out at a pathetic 11 knots. It was slow enough that a surfaced U-boat could catch it in a stern chase. When the blueprints were presented to President Franklin D. Roosevelt, a man who loved the Navy and considered himself an amateur naval architect, he was appalled. He looked at the high, awkward profile and the blunt bow and famously remarked to Admiral Emory S. Land, the head of the Maritime Commission, "I think this ship will do us very well." But then, turning to an aide, he muttered the verdict that would stick: "She is a dreadful-looking object." Time magazine was even less kind, dubbing the new ships ugly ducklings, but aesthetics were irrelevant. The only metric that mattered was speed of production. The goal was to build a bridge of ships across the Atlantic, a conveyor belt of steel that the Germans couldn't cut. To do that, the United States needed to revolutionize the very concept of shipbuilding. Before the war, shipbuilding was a craft. It was an art form practiced by men who had spent decades learning their trade. A ship was built from the keel up in a single spot of slipway. The process relied on lofting, where skilled artisans would lay out full-size templates of every hull plate on a massive floor. Then came the riveters. Riveting was the standard method of joining steel. It was a slow, labor-intensive, and deafeningly loud process. It required a team of 4 highly coordinated men, a heater to cook the rivet in a coal forge until it glowed white-hot, a catcher to catch the flying metal with a bucket or tongs, a holder-on to brace the rivet from the inside of the hull, and a riveter to hammer it home with a heavy pneumatic gun. A single ship required hundreds of thousands of rivets. It took months to build a cargo ship this way. The U.S. Maritime Commission knew that if they built Liberty ships the traditional way, the war would be over before the fleet was ready. They needed a disruptor. They needed someone who didn't know that what they were asking for was impossible. Enter Henry J. Kaiser. Henry Kaiser was a bald, rotund, cigar-chomping industrialist who looked like a caricature of American capitalism. He was not a shipbuilder. He had never built a ship in his life. He was a construction magnate, a man who had made his fortune paving roads in Cuba and building massive dams in the American West, including the Hoover Dam and the Grand Coulee Dam, Kaiser didn't care about maritime tradition. He cared about logistics. He viewed a ship not as a complex vessel, but as a collection of steel parts that needed to be assembled. To him, a ship was just a building that floated. When Kaiser approached the Maritime Commission, the traditional East Coast shipbuilders laughed at him. They called him a concrete man. They said you couldn't build ships with construction workers. Kaiser ignored them. He secured contracts to build shipyards on the West Coast, Richmond in California, and Portland and Vancouver in the Pacific Northwest. Kaiser's genius was to apply the logic of the Detroit assembly line to the shipyard. He looked at the bottleneck of the slipway. In a traditional yard, a keel would sit in the slipway for months while workers crawled over it, slowly building the walls and decks. This meant that a shipyard with 5 slipways could only work on 5 ships at a time. Kaiser blew this model apart. He introduced prefabrication on a massive scale. Kaiser realized that if you broke the ship down into smaller chunks, bow sections, deckhouses, double bottom tanks, you could build those chunks anywhere. You could build them in a factory 10 miles inland. You could build them in an open field. You could have 3 shifts of workers welding these sections simultaneously without getting in each other's way. The shipyard, in Kaiser's vision, became merely an assembly plant. The components would arrive by rail or truck, be lifted by gigantic whirly cranes, and dropped into place on the slipway. The ship wasn't built in the slipway. It was assembled there. This drastically reduced the time a keel occupied the valuable waterfront real estate. But prefabrication created a new problem. You couldn't easily rivet these massive pre-built sections together. It was too slow, and the alignment had to be perfect. Kaiser needed a faster way to join steel. He bet the farm on a technology that was, at the time, still viewed with suspicion by old-school naval architects: electric arc welding. Welding changed everything. A riveted joint requires overlapping plates, a lap joint, which adds weight and drag. A welded joint fuses 2 plates edge to edge, a butt joint, creating a smooth, lighter, and stronger connection. More importantly, welding was fast. A single welder could do the work of a 4-man riveting team. And crucially, a welder could be trained in weeks. A riveter took years to master. This allowed Kaiser to tap into a labor force that had never been used in heavy industry before. Since the skilled men were being drafted to fight, Kaiser hired everyone else. He hired farmers from the Dust Bowl. He hired sharecroppers from the South. He hired lawyers, artists, and waiters. And in a seismic cultural shift, he hired women. Rosie the Riveter became the icon, but in Kaiser's yards, she was Wendy the Welder. These women, who had been housewives or secretaries a month before, were given a crash course in running a bead of molten steel, handed a mask and a stinger, and sent into the bowels of the ships. The speed of production became a national obsession. The timeline for building a Liberty ship dropped from 240 days to 150, then to 100. In September 1942, Kaiser's Richmond yard pulled a publicity stunt that stunned the world. They laid the keel of the SS Robert E. Peary on a Sunday. By Thursday, the ship was launched. 4 days, 15 hours, and 29 minutes. It was a frenzy of sparks and steel. The paint was literally smoking as the ship hit the water because it hadn't had time to dry. The United States was producing tonnage on a scale that Nazi Germany could not comprehend. We were launching 3 ships a day. The U-boats were sinking them. Yes, but we were building them faster than they could reload their torpedo tubes. It seemed like the perfect victory of American ingenuity. We had stripped away the artistry and replaced it with brute force and speed. But in this headlong rush to save the world, the engineers had overlooked a critical, invisible detail. They had fundamentally changed the nature of the ship's structure, but they were still thinking in terms of the old physics. They had moved from a flexible, disjointed structure, rivets, to a rigid, monolithic one, welds. And they were building these monoliths out of a material steel that they didn't fully understand. The warning signs were there, buried in the noise of the production records. Throughout 1942, there were whispers. A welder would finish a seam, turn around to change his rod, and hear a ping. He would look back and see the weld he just finished crack down the middle. Foreman dismissed it as bad technique and ordered it re-welded. Ships on sea trials reported strange banging noises in the night. Captains complained of cracks appearing in the corners of hatchways, but the momentum was too great to stop. The cry was ships for victory, and anyone questioning the quality was accused of defeatism. The inspection bureaus were overwhelmed. They were certifying ships as one simply because they floated and the engine started. The pressure to clear the slipway for the next keel was intense, and so the Schenectady was built. Hull number 1, a symbol of the new T2 tanker program, bigger and faster than the Liberty ships, but built using the same methods, the same welders, and crucially, the same steel. When she snapped in half that night in Portland, the illusion of invincibility snapped with her. The fracture was not just a structural failure. It was a psychological shockwave. It proved that these ships were not just threatened by torpedoes and mines. They carried a fatal flaw within their own atoms. The massive steel plates, which looked so solid, concealed a treacherous secret that only revealed itself under specific conditions. The investigation that launched the next morning was frantic. The FBI was involved, looking for sabotage. The metallurgists were summoned. The welding inspectors were interrogated. But as they poked through the wreckage of the Schenectady, tracing the jagged line of the fracture that had turned a supertanker into a raft, they began to realize that the problem wasn't a bomb. It wasn't a Japanese frogman. It was something far more terrifying because it couldn't be shot at. The ships were allergic to the cold. The Schenectady had been sitting in 20-degree air. The water was frigid. The steel had contracted. And somewhere, deep in the microscopic lattice of the metal, a transition had occurred. The steel had ceased to be steel and had become glass. This was the beginning of the Liberty ship fracture crisis. It was a crisis that would threaten to undo the entire logistics strategy of the Second World War. As the fleet sailed north into the icy convoy routes of the Atlantic and the brutal storms of the Aleutians, the sailors were about to discover that the bridge of ships was brittle. The Schenectady was the first loud crack in the ice, but the storm was just beginning. The sinking of the Schenectady was a public embarrassment, a spectacle of failure, visible from the banks of the Willamette River. But the War Shipping Administration, WSA, had a powerful tool at its disposal: censorship. The true nature of the disaster was buried under a blizzard of bureaucratic euphemisms. The official reports hinted at a localized failure or exceptional loading conditions. They treated it as a freak accident, a one-in-a-million defect in a single keel plate. They assured the public and the sailors that the Liberty fleet was sound. But out in the Atlantic, far beyond the reach of press releases, the ships were telling a different story. And they were telling it with the sound of gunfire. As the winter of 1943 tightened its grip on the Northern Hemisphere, the convoys headed for Britain and Russia sailed into a meteorological buzzsaw. The North Atlantic is one of the most hostile environments on Earth. Waves can reach 40 feet. The wind screams constantly, but the real enemy wasn't the wind or the water. It was the temperature. The air temperature dropped well below freezing, and the water hovered just above 28 degrees Fahrenheit. In these conditions, the freak accident of the Schenectady began to repeat itself with terrifying regularity. It started with Group 1 fractures, the classification for minor cracks. A sailor on the morning watch would chip ice off the deck and find a fissure running from a hatch corner to the gunwale. Or a radio operator would report a strange pinging sound echoing through the hull at night, like someone tapping the steel with a hammer. These were the warning signs, the groans of a structure under torture. Then came the Group 3 fractures. Catastrophic failures. Consider the case of the SS Manhattan. She was a T2 tanker, a sister ship to the Schenectady. On March 29, 1943, she was leaving New York Harbor. The water was calm. She was fully loaded. She had just cleared the submarine nets and was entering the main channel when, without any warning, the ship stopped. She didn't hit a mine. She didn't lose power. She stopped because she was no longer one ship. A fracture had initiated in the deck, likely near a poorly welded scupper, and had traveled instantly down both sides of the hull. The ship broke cleanly in two. The bow section and the stern section drifted apart, floating like two separate icebergs. The crew, stunned and scrambling for life jackets, found themselves staring across a widening gap of water at the other half of their vessel. The SS Manhattan hadn't been battered by a storm. She had simply given up. The horror intensified in the Pacific. The SS John P. Gaines was a Liberty ship carrying supplies to the troops stationed in the Aleutian Islands, a desolate chain of volcanic rocks reaching toward Siberia. The route to the Aleutians is notorious for its violence. The water is freezing, and the storms are relentless. In November 1943, the Gaines was fighting a heavy sea. She was riding the crest of a massive wave, her bow and stern supported by the water, but her midsection hanging unsupported in the trough. This is known as hogging. The ship bends like a banana. In a riveted ship, the plates would have shifted slightly, the rivets would have groaned, and the energy would have dissipated. But the Gaines was a welded monolith, and her steel was cold. As she hogged over the wave, the tension on the main deck became unbearable. With a sound that survivors described as an explosion, the ship snapped. The fracture was so violent, it threw men from their bunks. The lights died instantly as the cables sheared. The ship broke into two distinct pieces. The forward section, heavy with cargo and lacking propulsion, sank rapidly into the freezing dark, taking 10 men with it. The stern section, containing the engine room and the crew quarters, remained afloat. For hours the survivors huddled on the tilting deck of their half-ship, drifting in the gale, waiting for rescue, listening to the ocean, battering the open wound of the hull. They were eventually saved, but the psychological scar remained. They had seen their ship murder their shipmates. By the end of 1943, the statistics were becoming impossible to ignore. Nearly 1,500 ships, almost half the fleet, had reported significant fractures. 12 ships had broken completely in two. 26 others had suffered such severe damage that they were declared total losses. This created a crisis of morale that threatened to break the merchant marine. These men were civilians. They were volunteers. They were already facing the highest casualty rate of any service branch, higher than the Marines or the paratroopers. They accepted the risk of U-boat torpedoes. That was war. They accepted the risk of Luftwaffe bombs. That was war. But they could not accept that the ship itself was trying to kill them. A dark folklore began to spread in the mess halls and union halls. Sailors called them Kaiser's coffins. They traded stories of ships that unzipped in the night. They whispered that the welding was done by housewives who were baking cookies last week. Sleeping below decks became an act of supreme courage. Men would sleep in their life jackets, fully clothed, with a knife in their pocket to cut themselves free if the hull buckled. Every time the ship slammed into a wave, a slamming event, the crew would freeze, waiting for the gunshot sound that meant the keel had snapped. In Washington, the engineering board of the Maritime Commission was in a state of controlled panic. They were staring at a disaster that could lose the war. If they had to ground the Liberty fleet, the supply lines to England and Russia would be severed. The invasion of Europe would be canceled. They needed to fix the ships, and they needed to do it without stopping the convoys. The investigation was launched with immense urgency. The best naval architects and engineers in America were summoned. They looked at the evidence. They looked at the Schenectady. They looked at the SO Manhattan, and they came to a conclusion that was logical, plausible, and almost entirely wrong. They blamed the locked-in stress, also known as residual stress. This theory became the gospel of the investigation. The logic was sound. Welding is a thermal process. You are using an electric arc to melt steel at 2,500 degrees Fahrenheit. When you deposit a bead of molten metal into a seam, it is liquid. As it cools, it solidifies and shrinks. If that cooling metal is constrained, if it is welded between two rigid heavy plates that cannot move, the shrinking metal pulls on the surrounding steel with tremendous force. The engineers calculated that the tensile stress locked into a weld could approach the yield point of the steel itself. In their minds, a Liberty ship wasn't just a metal box. It was a spring wound too tight. The hull was preloaded with tension before it ever hit the water. They believed that when the ship encountered the additional stress of a wave or a heavy cargo load, the combined force exceeded the limit and the metal snapped. This theory was seductive because it offered a solution that didn't involve scrapping the fleet. If the problem was locked-in stress, then the fault lay with the process, not the design or the material. It meant the problem was human error. The blame was shifted to the shipyards. The engineers argued that the welding sequences, the specific order in which plates were joined, were wrong. They claimed that the welders were working too fast, trapping heat, or welding against the constraint. A massive re-education program was launched. Inspectors descended on the yards like inquisitors. They drew up complex new welding maps. Don't weld the deck to the hull until the bulkheads are cool. Use a wandering sequence weld 3 feet here and move 10 feet away, then come back. They ordered, peening the practice of hammering a cooling weld to physically stretch the metal and relieve the tension. Millions of man-hours were spent trying to perfect the choreography of welding. The shipyards complied. The welders slowed down. The inspections became ruthless. And yet, the ships kept cracking. There was a chilling realization creeping into the minds of the top engineers. The theory didn't fit the facts. They found cracks in ships that had been welded perfectly. They found cracks in plates that had virtually no residual stress. And most damning of all, they found that even when they relieved the stress, the steel still failed in a brittle manner. But they couldn't wait for a new theory. The ships were breaking now. So, while the scientists argued about stress tensors, the Navy implemented a brute force mechanical solution. If they couldn't stop the cracks from starting, they had to stop them from finishing the job. They invented the crack arrestor. It was a humiliating admission of defeat for the proponents of the all-welded ship. The order went out to retrofit the entire Liberty fleet. The solution was to deliberately damage the ship to save it. Workers used acetylene torches to cut long slots through the deck plating and the hull, effectively slicing the continuous welded structure back into separate pieces. Then, over these slots, they installed massive steel straps. But they didn't weld these straps. They riveted them. They were reintroducing the discontinuity of the old 19th century designs. The theory was simple. If a crack initiates in the brittle welded hull, it will race through the steel at 6,000 feet per second. It will rip through the deck like a zipper. But when it hits the crack arrestor slot, it hits air. The crack cannot jump the gap. The energy dissipates. The riveted strap, which is mechanically separate from the hull plate, holds the ship together. It was a tourniquet. It didn't cure the disease. It just stopped the patient from bleeding to death instantly. The retrofit program was massive. Thousands of ships were pulled into repair yards. The decks of the Liberty ships, once smooth and flush, were now scarred with these heavy, ugly steel belts running along the gunnels and the hatch combings. To the sailors, these straps were a visual reminder that their ship was fundamentally broken. They were riding a vessel that had to be literally strapped together to keep from falling apart. But the crack arresters worked. They didn't stop the cracking fractures continued to plague the fleet, but they stopped the total failures. Ships would come into port with a 6-foot crack in the deck, stop dead at the riveted strap. The bow was still attached to the stern. The cargo was delivered. Yet the mystery remained. The locked-in stress theory was bleeding credibility. Why did the cracks only happen in cold water? Why did the steel shatter like glass instead of tearing like taffy? Why did the fractures look crystalline under a microscope? The American engineering establishment was running in circles, obsessed with welding techniques and stress diagrams. They were looking at the geometry of the ship. They should have been looking at the chemistry. While Washington argued, a crate containing jagged, broken pieces of steel from a fractured Liberty ship was loaded onto a transport plane. It was flown across the Atlantic to a country that had been building steel ships for a century. It was delivered to the Cavendish Laboratory at Cambridge University, to a department that didn't care about welding schedules or tonnage quotas. It ended up on the desk of a woman named Constance Tipper. She was about to look into the heart of the metal and find the monster that the Americans had missed. The problem wasn't how the ships were built. The problem was the ships themselves. The arsenal of democracy had been forged from poison steel. While the North Atlantic continued to grind the Liberty fleet into scrap metal, and while the shipyards of Oregon and California welded steel bandages onto the hulls of their creations, a small wooden crate arrived in Cambridge, England. It had traveled across the ocean on a bomber priority cargo, passed from the U.S. Maritime Commission to the British Admiralty. The label on the crate was nondescript, but the contents were evidence from a crime scene. Inside were jagged, heavy chunks of steel plate cut from the fractured hull of a Liberty ship. The crate was delivered to the Cavendish Laboratory, the hallowed ground of British physics. This was the place where the electron was discovered, where the atom was split. But the recipient of this package wasn't looking for subatomic particles. She was looking for cracks. Her name was Dr. Constance Tipper. In 1943, Constance Tipper was a statistical improbability. A reader in mechanical engineering at Cambridge, she was a woman operating at the highest level of a profession that was overwhelmingly, aggressively male. The world of naval architecture was a club of admirals and industrialists who smelled of cigar smoke and welding flux. Tipper belonged to a different world, the world of crystallography. She didn't look at ships as floating warehouses. She looked at them as arrangements of atoms. She studied the microscopic lattice structures of metals. When the Admiralty asked her to examine the American steel, the U.S. engineers were already convinced they knew the answer. They were still married to the locked-in stress theory. They believed the steel was fine. After all, it was American steel, made in the mighty blast furnaces of Pittsburgh and Gary. It met every specification. It passed every standard test. They assumed Tipper would simply confirm that the welding had introduced too much tension. Tipper took the samples to her lab. She didn't start by measuring the stress. She started by looking. She placed the fractured surfaces under a microscope. What she saw immediately contradicted the American narrative. If a piece of steel breaks because it has been pulled apart by tension, like the locked-in stress theory suggested, the fracture surface looks rough, gray, and fibrous. It looks like torn taffy. This is a ductile fracture. It means the metal grains stretched, deformed, and finally tore away from each other. It's a warning. The metal fights back before it dies. But the steel from the Liberty ship looked different. The fracture surface was bright, shiny, and faceted. It sparkled under the lab lights. It looked like broken sugar or shattered glass. Under high magnification, she saw what are known as river markings, tiny lines radiating out from the origin of the crack. This was a cleavage fracture. The crack hadn't torn through the metal. It had sliced right through the grains themselves. It had traveled along the crystallographic planes of the atoms. To Tipper, The diagnosis was instant and terrifying. The steel hadn't stretched. It had shattered. It was brittle. This conclusion presented a paradox. How could steel that was proven to be ductile in the American factories become brittle in the middle of the ocean? Steel doesn't just change its personality. Or does it? Tipper realized that the standard tests used by the U.S. Navy and the classification societies, like the American Bureau of Shipping, were fundamentally flawed. They relied on the static tensile test. You take a bar of steel, put it in a machine, and pull it slowly until it breaks. It's a slow, steady torture. Under these conditions, at room temperature, the Liberty steel behaved perfectly. It stretched. It was tough. But the ocean is not a laboratory. The ocean is dynamic. Waves don't pull slowly. They strike. They impact. And crucially, the Atlantic Ocean is cold. Tipper devised a new experiment. She moved away from the standard tensile test and developed a notch test, a precursor to the modern Sharpie V notch test. She took strips of the Liberty steel and cut a small notch in the side. This notch represented the real-world flaws found in every ship. A bad weld, a square hatch corner, a sharp discontinuity. The notch was a stress concentrator. Then, instead of pulling the steel, she struck it. And she did it at different temperatures. She started at room temperature, around 60 degrees Fahrenheit, 15 degrees Celsius. The steel held. It deformed around the notch, absorbing the energy of the blow. It was ductile. Then she lowered the temperature. She cooled the samples to 50 degrees. 40 degrees. As the thermometer dropped, she saw a dramatic transformation. The energy required to break the sample didn't decrease gradually. It fell off a cliff. At a certain critical temperature, around 32 degrees Fahrenheit, 0 degrees Celsius, the freezing point of water, the steel underwent a metamorphosis. It lost all its toughness. When she struck the cold sample, it didn't bend. It snapped instantly, with a sharp crack, leaving behind that telltale shiny, crystalline surface. Tipper had discovered the ductile to brittle transition temperature, DBTT. She realized that the Liberty ships were made of a Jekyll and Hyde material. In the warm waters of the South Pacific, or during the summer sea trials in Portland, the steel was Dr. Jekyll, strong, flexible, safe. But as soon as the water temperature dropped below that critical transition point, which happened to be exactly the temperature of the North Atlantic convoy, roots the steel became MR Hyde. It became a ceramic. It became glass. A ship made of this steel could survive a torpedo in the tropics, but could be destroyed by a wave in the Arctic. The question then became, why? Why was American steel so sensitive to cold? Tipper, working with metallurgists, traced the problem back to the chemistry of the arsenal of democracy. In the frantic rush to produce steel for tanks, ships, and guns, the U.S. mills were pushing their production to the absolute limit. They were using the open hearth process, but they were running it fast. To save time and money, and because of shortages of certain alloys, the chemical composition of the steel had drifted. The culprit was a specific ratio of elements. The Liberty steel was high in carbon, which makes steel strong but brittle. More importantly, it was high in sulfur and phosphorus. These are tramp elements, impurities that weaken the grain boundaries of the metal. In high-quality peacetime steel, these are removed, but removing them takes time and money. In wartime, the specifications were loosened. The manganese content, an element that helps toughen steel and lower the transition temperature, was too low. The result was dirty steel. It was a chemical cocktail that raised the transition temperature from a safe minus 20 degrees Fahrenheit down to a dangerous plus 30 degrees Fahrenheit. The steel was technically up to spec, but the spec was wrong. When Constance Tipper wrote up her report, she knew she was dropping a bomb. Her conclusion was stark. The fractures are not due to welding. They are not due to design. They are due to the material itself. The steel is cold short. It is unsuited for service in cold water. The reaction from the other side of the Atlantic was not gratitude. It was denial. The battle of the metallurgists began. It was a clash of cultures, genders, and egos. The American engineering establishment, led by the heavyweights of the Maritime Commission, refused to accept that their steel was defective. To admit that would be to admit that the entire U.S. industrial effort was producing a flawed product. It was a political impossibility. They attacked Tipper's methods. They argued that her notch test was artificial, that ships didn't have notches, a ludicrous claim given the quality of the hasty welding. They argued that her samples were too small to represent a 10,000-ton hull. And implicitly and explicitly, they dismissed her because she was a woman. One American admiral famously read her report and tossed it aside, grumbling about British academic nonsense. They clung desperately to the locked-in stress theory. They continued to blame the welders. They continued to change the welding sequences. They continued to insist that if they just built the ships better, the steel would hold. But science is stubborn, and the ocean was on Tipper's side. Throughout 1944, the data started to make the American position untenable. The correlation was undeniable. Fractures peaked in January and February. They peaked on the northern routes. Ships that had sailed safely for years in the Caribbean would snap as soon as they were reassigned to the Murmansk run. Furthermore, the crack arresters provided the final piece of proof. The riveted straps were working. When a crack ran through the welded hull, it stopped at the strap. Why? Because the strap was a different piece of steel, often of a different grade, and it wasn't part of the continuous brittle matrix. If locked-in stress was the problem, the straps shouldn't have mattered. The fact that the crack propagated through the base metal, but stopped at a mechanical joint, proved that the base metal was the highway for the failure. Slowly, reluctantly, the giants of American industry had to bow to the woman from Cambridge. The Bureau of Standards in Washington began to replicate her tests. They found the same curve. They found the same cliff. The transition temperature was real. The victory of Constance Tipper was absolute, but it was a silent victory. There was no press conference. There was no public apology. The implications were too terrifying to share with the public. You couldn't tell the merchant mariners that the steel beneath their feet was chemically programmed to fail in winter. Instead, the solution was implemented quietly, almost secretly. For the thousands of Liberty ships already built, nothing could be done except to add more crack arresters and issue new sailing orders. Avoid heavy seas where possible, an absurd order in the middle of a war, and ballast the ship to reduce bending moments. But for the new generation of ships, the Victory ships, that were starting to replace the Liberties, the rules were rewritten. The chemical specifications for ship steel were changed. The carbon content was lowered. The manganese content was raised. The limits on sulfur and phosphorus were tightened. The Tipper test, which evolved into the Charpy V notch test, became a standard requirement. Constance Tipper had solved the mystery. She had proven that the Schenectady didn't break because of a bad welder. It broke because the laws of physics dictate that impure steel becomes glass at freezing temperatures. She had saved the future fleet, but the existing Liberty ships were left to their fate. They were now known quantities flawed warriors, bandaged with steel straps, sailing on borrowed time, fighting a war against the Axis, while their crews prayed that the thermometer wouldn't drop too low. As the war entered its final bloody year, these ships would be pushed to their breaking point. And while the science was now understood, the danger was far from over. The legacy of the Liberty ships was about to shift from a story of wartime failure to one of the most remarkable and dangerous commercial gambles in history. August 10th, 1945. The guns fell silent. The Imperial Japanese Navy had ceased to exist, and the U-boats were surfacing to surrender, flying black flags. The Second World War was over. The United States emerged from the conflict not just as a victor, but as the undisputed industrial master of the planet. And floating in the harbors of the Pacific, the Atlantic, and the Mediterranean was the physical proof of that dominance. The Liberty Fleet, over 2,700 Liberty ships had been built. They had carried the grain that fed Britain, the tanks that liberated France, and the bombs that leveled Germany. They were the most successful mass-produced complex object in human history. But they were built with a very specific expiration date. The design specification for the EC2, SC1 had called for a service life of 5 years. They were expendable munitions, calculated to survive just long enough to make a profit on the balance sheet of war. If a ship made 1 or 2 crossings before being torpedoed, it was considered a success. Now, suddenly, there were thousands of them left. And they were tired. They were battered by years of convoy duty, rusted by the salt spray, and as Constance Tipper had proven, built of steel that was chemically unstable in cold water. The United States government faced a massive logistical headache. What do you do with 20 million tons of shipping that you no longer need? The initial solution was the mothball fleet. In rivers and bays across America, in the James River in Virginia, Sassoon Bay in California, the Hudson River in New York, the Navy anchored the ships in long, silent rows. They stripped the guns, drained the boilers, sealed the hatches, and left them to rust. These became the ghost fleets, miles of gray steel hulls bobbing quietly in the current, a graveyard of the arsenal of democracy. But the world economy was destroyed, and it needed to be rebuilt. Europe was starving. Its railways were bombed out. Its merchant fleets were at the bottom of the ocean. There was a desperate, insatiable hunger for raw materials, coal, grain, iron ore, timber. The only ships available to move these mountains of cargo were the Liberty ships sitting in the American rivers. The U.S. Congress passed the Merchant Ship Sales Act of 1946. It was a fire sale. The government decided to sell the surplus ships to allied nations and private shipping companies for a fraction of their construction cost. You could buy a Liberty ship, fully functional, for about $500,000 pennies on the dollar. This sale created a unique opportunity, and it was seized by a group of men who would become legends of the 20th century, the Greek shipping magnates. Men like Aristotle Onassis, Stavros Niarchos, and Kostas Lemos saw what the major established shipping lines missed. The big companies Cunard, U.S. lines looked at the Liberty ships and saw junk. They saw slow, ugly, obsolete steamers with a terrifying reputation for breaking in half. They wanted new, fast, turbine-powered ships. But Onassis and Niarchos saw a gold mine. They understood the risk, but they also understood the math. They realized that the Tipper revelation, the discovery of the brittle steel, didn't mean the ships were useless. It meant they had operational limits. These tycoons bought the Liberty ships by the dozen. They built their initial fortunes on the backs of these dangerous vessels. They applied a brutal, pragmatic logic to the operation. They knew the steel became glass in the cold, so they simply changed the map. They routed their Liberty fleets to the warm waters of the Persian Gulf, the South Atlantic, and the Mediterranean. They carried oil from Saudi Arabia and grain from Argentina. They avoided the North Atlantic in winter like the plague. They also invested in beefing up the hulls. They took the crack arrestor concept and expanded it. They welded massive doubler plates over the shear strakes and the deck stringers. These were thick belts of high-quality steel that acted as external armor for the ship's spine. They essentially strapped the ships together so tightly that the brittle base metal couldn't move enough to crack. It was a gamble. Every time a Liberty ship left port under the flag of Onassis or Niarchos, it was a roll of the dice. But the gamble paid off spectacularly. The post-war economic boom was fueled by these ships. The Liberty ships, designed to last 5 years, ended up sailing for 20, 30, even 40 years. They became the tramps of the global ocean, chugging along at 11 knots, carrying the low-value cargoes that the sleek new liners wouldn't touch. They were rusty, they leaked, and they rattled, but they refused to die. However, not every ship survived the transition to peace. The plague of glass had not been fully cured, only managed. In 1947, the SS Sankey, a British-operated Liberty ship, disappeared without a trace in the Atlantic. No distress signal, no wreckage, just gone. The Court of Inquiry concluded that she likely suffered a catastrophic structural failure in a storm and sank so fast the radio operator never had a chance to key the mic. In 1948, the SS Leicester was abandoned in a hurricane after she developed a severe list. When salvage tugs found her, they discovered massive cracks in her hull. The ocean was still claiming its tax on the wartime steel. But the most enduring legacy of the Schenectady and the Liberty ship fractures is not found in the shipping lanes. It is found in the textbooks of engineering. The disaster forced a fundamental rewrite of how humanity builds structures. Before World War II, the philosophy of engineering was based on yield strength. Engineers asked, how much load can this beam take before it bends? They assumed that if a material was strong enough to hold the weight, it was safe. They treated steel as a monolithic, perfect material. They assumed that if you built a ship with a safety factor of 2, making it twice as strong as necessary, it would never break. The Liberty ships proved that strength and toughness are two completely different things. Glass is strong. It's hard to scratch, but it has zero toughness. It shatters. Rubber is weak, but it has high toughness. It stretches. The Liberty steel was strong, but in the cold, it had the toughness of a ceramic plate. This realization birthed the modern science of fracture mechanics. Because of the Liberty ships, engineers began to understand that all structures contain flaws. There is no such thing as a perfect weld or a perfect plate of steel. There will always be a microscopic crack, a bubble, an inclusion. The goal of engineering shifted from preventing all cracks, which is impossible, to managing the cracks. This led to the concept of critical crack length. For every material, at every temperature, there is a specific size of crack that is stable. If the crack stays smaller than that size, the structure holds. If the crack grows just 1 millimeter beyond that limit, the energy required to extend the crack drops to 0, and the crack travels at the speed of sound. In the Liberty ships, in cold water, the critical crack length was terrifyingly small, sometimes just a few inches. A tiny flaw could trigger the end of the ship. Today, this science keeps you alive. When you step onto a Boeing 787, or drive across a suspension bridge, or ride a high-speed train, the materials in those structures have been tested using the lessons learned from the Liberty fractures. The Charpy V-notch test, the direct descendant of Constance Tipper's hammer experiments, is now a global standard. You cannot build a bridge, a pipeline, or a ship's hull today without proving that the steel has sufficient notch toughness at the lowest operating temperature. The steel used in modern submarines, like the HY80 and HY100 alloys, is chemically formulated to remain ductile even in the crushing, freezing depths of the Arctic Ocean. We figured out how to keep the Mr. Hyde transformation from ever happening again. And what of the ships themselves? Of the 2,710 Liberty ships built, only 2 remain operational today. One is the SS John W. Brown in Baltimore. The other is the SS Jeremiah O'Brien, docked at Pier 45 in San Francisco. If you visit the Jeremiah O'Brien, you are stepping into a time machine. The ship is a living organism of 1943. The engine room is a cathedral of hot oil and steam, dominated by the massive triple expansion engine that still thumps with the heartbeat of the war. But if you walk up to the main deck and you look closely at the gunnels, you will see the scars. Running along the edge of the deck, riveted into the steel, is a heavy iron strap. It looks out of place, like a patch on a pair of jeans. It is the crack arrestor. It is the physical evidence of the panic of 1943. It is the bandage that the engineers applied when they realized their miracle ships were flawed. These ships are no longer viewed as ugly ducklings. They are revered as sacred spaces. The Jeremiah O'Brien actually returned to Normandy in 1994 for the 50th anniversary of D-Day, sailing across the Atlantic on her own power, crewed by a volunteer force of octogenarians, the same men who had sailed her as teenagers. When she arrived off the coast of France, she was the only ship in the Armada that had actually been there in 1944. The story of the Liberty ship is the ultimate story of the industrial age. It is a story of a calculated trade-off. To win the war against fascism, the Allies had to break the rules of perfection. They chose speed over safety. They chose quantity over quality. They accepted the grim calculus that some ships would snap in half and some men would drown, so that thousands of other ships could get through to deliver the blow that killed the Third Reich. It was a bargain made in blood and steel. The ships won the war, but the ocean exacted its price. And every modern structure, from the skyscraper to the space station, owes a debt to the sailors who went to sea in Kaiser's coffins, unknowingly testing the limits of metallurgy with their lives. The Liberty ships were built to die. The fact that they lived long enough to save the world, and then lived on to build the global economy, is the true miracle. They were flawed, they were dangerous, and they were magnificent. Subscribe to Maritime Tailies, because every rivet, every weld, and every crack in the steel tells a story of the price we paid to conquer the sea.